Hi, my name is Amy Zhang, and today for my 10-701 extra credit, I will be presenting active learning. Active learning is a type of semi-supervised machine learning. This means that instead of having labels for data, the algorithm can query the user or the environment for labels to some data. For example, the algorithm could query the user as to whether a particular message is spam in order to build a spam filter. Another example might be a robot exploring an environment. The robot can query the environment for particular sensory information in order to build a model of the world. Today, I'd actually like to focus more on active reinforcement learning. Reinforcement learning is using rewards to build that model and learn about the world. Therefore, active reinforcement learning needs to consider both how to explore the world, but also how to build a model that will maximize the amount of reward that we get. This is often done by Q-learning. Consider an MDP, a Markov decision tree. In order to simplify my diagram, I'm not going to draw the arrows. I'm going to consider a Markov decision process in which each square in this grid here is a state. And from each state, we can take actions that will move us to other states. The +1 indicates this is a state in which, is a terminal state in which we gain a reward of 1, and the -1 indicates that we gain a reward of -1. To formalize this, let's consider a Markov decision process with states, actions, and rewards. We are also going to want to consider gamma, a discount factor that indicates how interested we are in short-term versus long-term reward. A small gamma indicates that we're being very short-sighted, whereas a gamma closer to 1 indicates that we are looking further into the future. We also want to consider an alpha, which is going to be our learning rate. We want to learn a lot from new information. We should have a higher alpha. The utility of a state and an associated action should be equal to whatever reward we get at that state using that action, plus the discounted reward that we're going to get in the future. If we act ideally on the world. So we want to take the max of all actions that we could perform in the future and discount that, add that to our current reward. However, we don't really know enough about the world to just say this. We don't know what action will lead to which state with which probabilities. So in practice, we have to update Q iteratively. What we need to do is update Q iteratively. So if T is what time step we're on, we're going to want to change it from some amount that it was before. And we're going to want to change it scaled by whatever we determined our learning rate alpha would be. And here we want to have whatever the change in what we know now is. This actually should look pretty familiar because we just saw how we learn what we know now. This here is going to be the reward that we've gotten plus our discounted max over all of our possible actions of what the what we had before, and we're going to subtract that from what we knew before to create, this is the change. This is what we've learned. If we were very concerned about exploring, we could reject this action with some probability and take a random action instead. However, in the long term, this will converge to the optimal action to take at each state. And so we can explore what our expected reward is under a particular policy, where our policy might be to choose the optimal move. Well, the reward is going to be how much reward we expect from the current. We expect currently plus our future reward, which is the discounted. There's actually going to be gamma and alpha here, but I'm going to simplify this and just use one parameter, reward, in our next time step. Gamma squared times our expected reward 2 time steps from now. R equals 2, etc. Notice that we can rewrite this be the expected reward in our current time step plus gamma times the expected total reward for the future from the next time step. This allows us to not only discuss the expected reward for particular actions, but we can discuss what the value that we should associate with a particular state is under the optimal policy. So the value of state X under the optimal policy is going to be the max across all of the actions that we can take times, of the sum over the rewards we might get currently, in terms of probability of that reward, plus the discount of the sum for all other states that we could get to, the value at that state times the probability that we get to that state. So for example, if we traverse this Markov process, let's say our gamma and our alpha are both equal to 0.9. And we started our start state, we go through the process. I'm just going to consider, let's say we take this path. Next time, we go from this state to this reward state. We've learned that there's a reward there. And we can up 9 to 9 times 1. And it will also be have a Q value of 0.81. So the next time that we try and reach this state, we can update the state before it to be 9 times 9 times 0.81 is about 0.6, and it will have a Q value of about 0.6. We can do this for every possible action and every possible state in our MDP. Notice that there's an interesting complexity trade-off here. We're not learning the entire MDP at once, which would be a very expensive process. We're only updating the particular state that we're at, and we're doing an amount of work at each state proportional to the number of actions that we can take at each state. And that is one way you could do active reinforcement learning.